Hello students, now we will look into a relatively simpler way to solve these problems of linear programming using simplex method, and we will consolidate those concepts in form of table, and this method is called as Tableau method to solve simplex problems. Now what we will do here is that this is the same problem that 2x1 plus x2 minus x3 less than equal to 2, 2x1 minus x2 plus 5x3 less than equal to 6, and so on, and our objective function is to minimize subjected to these constraints. I have already introduced slack variables from our previous video, which are x4, x5 and x6 in this case. So we will make a nice table, and here we would have these titles of these columns as the variables involved, and this variable would involve x1 x all the way till x6, as well as minus f, which is the value of function that we will get as we will solve this tableau. Then BIs will collect all the values that are listed on right hand side, and we will calculate the ratio BI upon AR, which will become clearer. And if you remember from our last video, we were calculating this BI upon AR as 2 upon minus 1, or 2 upon 1, 6 upon minus 1, and 6 upon 1, and so on. So this would be constitute our ratios that I am talking about, because we were equating it to 0. So we were saying that maximum value x2 can take is just 2 by 1. X2 would is unbounded in this case, and similarly x2 was coming out to be 6 divided by 1. Whatever was the coefficient was going beneath. So we will do it in organized way and apply the same principles that we learned in all the concepts that we learned in previous video. And if you also see here, we have three columns, and these three rows, these rows would correspond to the basic variable that we have selected. And the first tableau from where we would begin would call as tableau 1. And the basic variables that we will choose is x5, x4, x5 and x6. So x4, x5, x6. In this table, we will populate all the coefficients associated with that particular row in which our basic variable is situated. So x4 is here. So we will have 2, 1, minus 1. So I will write it in a compact form. 2, 1, minus 1, 1, 0, 0. 2, minus 1, 5, 0, 1, 0, 4, 1, 1, 0, 0, 1. And here we have minus f, where we write minus 1, minus 2, minus 1, 0, 0, 0. Minus f has the coefficient of 1 in this case. And finally, BIs come out to be 2, 6, 6, 0. And minus f is not present in any of the constraints, we can simply write it as 0, 0, 0. Now our first tableau is complete except the last column. So we will see that how we can do that. First of all, since this is a minimization problem, we have to identify what should be our entering variable. Entering variable is the one which has the maximum negative coefficient, which in this case is minus 2. And once this goes on, we define that this is going to be our next pivot column. So we will highlight our next pivot column here. Also, what is going to be our next pivot row, that would be decided by the exiting element. To do that, once we determine what is our entering variable, we will take this bi and divide it by the corresponding value in the pivot column. That would be our new pivot column. So this would be 2 divided by 1. This would be minus 6. This is 6. We mentioned that we are looking for minimum of bi upon ai subjected to this ar is greater than 0. So minimum value would govern that who should be leaving. So if this was 2, we would not consider negative values, because here ar itself is negative, and in this case this comes out to be 6. Since this is the minimum value, this should leave, this would leave, and this would enter, and the row corresponding to leaving variable becomes our pivot row. So we will highlight this. And now what we will do is that once we have decided our leaving variables and entering variables, we will make a tableau 2. And in tableau 2, we will replace x4 by x2 because x4 has left and is no longer our basic solution, as we have made that a non-basic variable by forcing it to 0 by introducing x2. So our tableau 2 looks like, we will replace this x4 by x2, and now we will do pivoting about x2 because whatever is entering we should do pivoting about that. But when we do pivoting, all the values in this table will get jumbled up, and we know that from one pivot to another pivot we can easily go by applying some row transformation. So here is the golden rule or a shortcut that how we can do this pivoting operation really fast. So the rule is, for all elements outside pivot row and pivot column, the updated value E hat is given by E minus value in corresponding pivot row multiply by value in corresponding pivot column divided by pivot element, where pivot element is the intersection of pivot row and pivot column. Now, this is nothing special because when you are going from one pivot form to another pivot form, even if you do this manually, this is the transformation that you are implicitly applying again and again when you are doing row transformation. I have just simplified it using this expression. So we will not touch our pivot rows and pivot columns first, but we will change all the values surrounding that. So in that case, this would become 2 minus pivot row corresponding to this 2 is this one. So 2 multiply by pivot column is minus 1 into minus 1 divided by pivot element, which is 1 in this case here. So this becomes 2 plus 2 equal to 4. So I will just clean it a bit that now we have calculated it. So this is equal to 4. Now I will go to this element. Again, I will do the same calculation. 5 minus minus product of minus 1 and minus 1 would be plus 1. I mean positive 1, and this element becomes 4. Similarly, I will update this 0. Again, this would remain 0 by applying the same multiplication. This into this, these two divided by 1 and subtract from the old value. So this would become 0 plus 1, which is 1 in this case. So we are going 4, 4, 1. You can calculate all the values similarly. So this becomes 1, this is 0, this is 0, and this is updated as 8. Then we will update this column. This would become 2, this would become 2, this would become minus 1, 0, 1, 0, 4. And we will also update the values here. This becomes 3, this becomes 0, or this becomes minus 3 actually. So if you again do minus 1 plus 2, so this would be minus 1 minus minus 2 into minus 1 divided by 1, minus 1 minus 2 equal to minus 3. So this is minus 3, this is equal to 2, this is 0, 0, 1, and 4. I have not touched the pivot rows and pivot columns yet. I will come to them just now. What we will do here is that we would make this, we will do pivot operations about x2 now. That would mean that we should leave 1 here and zeros would come here. So we will reduce these to zeros. And coming to x2, we would divide all the elements of pivot row by our pivot element. So this would become 2 divided by 1 equal to 2 because our pivot element is 1. This will stay as 1, minus 1, 1, 0, 0, 0, and 2. And now I will erase all the blue values and some rough calculations that I did here so that this table becomes little cleaner. And this becomes our tableau 2. We have not calculated these values yet. I will come to these revised values. So we would not divide bi by ai, just our calculations would be limited to x and b's, as and of course the f also. So if you see that the solution or the beauty to work in always in canonical form is that whatever variable we have here and whatever value you see here, that is going to be the solution directly. So you see here in this case our x2 is 2, x5 is 8, x6 equal to 4, and value of function is equal to -4. In previous tableau, our function of values of function was 0. So we have definitely went from f equal to 0 to f equal to -4, which is definitely improvement as we are looking for minimization. All our variables are greater than 0 because x2 is great, x2, x5, x6, they are greater than 0. On the other hand, x1, x3 and x4, they are equal to 0. So far this is basic feasible solution and solutions are also improving. And this is the updated canonical form that we have. So we have 1 0 0 here, 0 1 0 here, 0 0 1 here. So x2, x5, x6 together constitute the canonical form. Now, still there is a scope of improvement. How I came to know about that? So if you see, even in the updated coefficient, we can have one more entry. That means x3 should enter now because it has the negative coefficient. And if we increase the value of x3 from anything above 0, solution can be brought down further. So we will bring this as an entry variable, and now we will identify the second exit variable. Last time we made x4 exit. This time let's see who exits our table. So again, I will repeat these calculations so that if you missed it first time, you should be able to get it. So I'm saying this is entering. We will again calculate these ratios only where the corresponding values in these columns are positive. Now I can write this as 2 divided by -1 not defined, 8 divided by 4 is equal to 2, 4 divided by 2 is equal to 2. And who should leave? Whatever value of bi upon ar is minimum, that should leave. Here x5 and x6, they have a tie, so we can arbitrarily choose who should leave here. So we are saying let us make x5 leave. As soon as we make x5 leave, this becomes our pivot row. And now we will apply the similar operation, that we will update this value of 2 from 2 minus 4 into -1 divided by 4, and as a result of which this value becomes 3 because 4 and 4 cancels out and 2 plus 1 becomes 3. We will update the next value. It would come as 1. This becomes 5 by 4. Next to 5 by 4 we get 1 by 4. This stays 0, 0, and here we get 4. We will come to second row, which is our pivot row later. So let's update this 2 first. This would become 0, this would become 0, minus 1 would be updated to minus 3 by 2, 0 would be updated to minus 1 by 2, this is 1, this is 0, and this is also 0. We will update these values here. Again, I am applying the same formula. So I am saying that updated value would be 3 minus 4 into -3 divided by 4. So this becomes 3 plus 3 equal to 6, because here this is our element, this is our complete extension of pivot column. So this -3 comes from here, and 4 comes from here, and pivot element is also 4. From after 6 we get 0, and we will come back here later again. This becomes 11 by 4, this becomes 3 by 4, this becomes 0, this becomes 1, and this becomes 10. Again, I will erase all the values that are written in red to make a cleaner tableau, and I will come to pivot columns once I make this little cleaner. and here I will delete this and so on. Now coming to the pivot column again, so let us remove this highlight to make it clear. We will divide all these values by the pivot element in the pivot row. So this would become 4 divided by 4 1. This would be 0. 0 would remain 0. This would become 1 by 4, this would become 1 by 4, this is 0 0, and this becomes 8 divided by 4 equal to 2. And again I will remove all these elements that are written in a red as I move towards the updated tableau, and these do not have significance now as we have changed the values and they were corresponding to our previous tableau. And coming to our pivot column, what we will do here, about what we are pivoting, we will make this as 1. So this was our pivot element, so this should be 1 and we should have 0 everywhere else. So this is 0, this is 0, and here we also have a 0. Now you see that once we have updated our new tableau, the value of f comes out to be minus 10, x2 has the value of 4, and also we, so now this was x2 x5 x6, we had an entry variable here, so x5 left, so instead of x5 we have x3 now. So x2 has value of 4, x3 has value of 2, and x1 has value of 0, x6 has value of 0, x4 also has value of 0, and so on. So in our objective function, we are only concerned about x1, x2 and x3. So when we plug the values here, we get the value of objective function as minus 10, and you can simply check it out also by plugging these values into minus x1, minus 2, x2, minus x3. Now once we have updated this, and all the values are changed, who should enter next? Now there is no coefficient which is negative, and bringing anything in is not going to improve our solution further. So we say that our iteration stop now. Our iteration stop because there is nobody who can enter now. So the optimal value of this function is minus 10, corresponding to x2 equal to 4, x1 0, and x3 equal to 2. And this is a bounded solution. In next video, we are going to talk about unbounded solution, but I request you to watch this video multiple times, try to do these calculations by yourself, and things would become very clear, as this is a very simple and easy way to implement the linear programming problem. Thank you.